All right, ladies and gentlemen, the witty banter is over and class recording has started. So yesterday, we looked at the graphs of an object that was pretty close to being in free fall or under the influence of gravity. And in case you don't remember, these are what they looked like. So this was the graph of the volleyball that we did yesterday. And we talked about analyzing that graph, and we then looked at the velocity graph and the acceleration graph, and we got the slope of the velocity graph, and we figured out the average acceleration, and we got everything, all the things we needed about the flight of that ball, right? So we talked about the idea that, from here to here, the entire time that velocity graph is above the x-axis, meaning that the ball was going upward the entire time, sometimes speeding up, sometimes slowing down, but always upward. And then from here to here, right, the velocity graph always underneath the x-axis, so the velocity values are negative, sometimes speeding up, sometimes slowing down, but always moving downward. And that's what we see as far as the part of the position graph and how it comes together, right? In looking at the acceleration graph, we'll auto scale this. So we said that's what the acceleration graph looked like. During this section right here, we see that the acceleration is fairly constant. Some bumps up and down, but fairly constant during that section. And we said that if you look at the position graph, that's the flight of the ball, right? That's when it's going up and coming back down. But it did have these two big spikes in it. And we talked about the idea that if I were to zoom in on like that big spike right there, that's right when that ball, the position graph of the ball, is starting to move upward. So these two big spikes here, and then this one here at the end, right? Really right when that ball returns back to where it was originally starting. Those two big spikes in the acceleration graph are the result of what? Why are they there? That's me throwing and catching the ball, right? I'm giving acceleration in the positive direction because I was pushing upward to throw the ball. And then when it got back, the spot that's highlighted here, it's coming back down, but I have to push up on it to stop it, right? So those two big spikes, that's me. But then the rest of the time, from here to here, right, that's gravity, okay? Good there. One last thing, just to sort of, and we talked about taking the average of this acceleration here, and when we took the average acceleration, it came out to be, what did we get? Negative 9.342. That's what we got for the average acceleration value during that time. Okay. All right. So let's go and let's answer some questions about this lab. Okay. Let's start on the front page because there's a couple of preliminary questions that we didn't answer. We drew the pictures at the bottom, but we didn't answer the other preliminary questions. So, I realized that we're supposed to do preliminary questions before we do the lab, but whatever. So. All right, number one, I hope we can answer this one pretty easy. What's responsible for making the object slow down on its way up and speed up on its way down? Gravity. Number two, how does the acceleration of the object on the way up compare to the acceleration of the object on the way down? One's slowing down, one's speeding up. That's what's happening to the velocity, right? But what did we say about the acceleration values? Elise? Even on this picture, right, if we go back here, right, this part, or here, let's do this, right? Graph, auto scale. Wish I could zoom in on this a little easier, right? We said that this is the up trip of the ball. That's after it leaves my hands on its way to the top. What do you see about the acceleration during that time? Fairly constant, right? But then from here to here, right? That's the down trip, right? What do you see about the acceleration during that time? Constant. How does it compare to the previous part? Exactly the same. So the acceleration on the up trip is exactly the same as the acceleration on the down trip. Why? What's causing that acceleration? What's causing the ball to slow down on the way up and speed up on the way down? Gravity. Gravity's always acting on it, regardless of whether it's going up or coming back down. And it's always acting on it, causing the same acceleration, right? Regardless of the direction that it's moving. Krista, does that answer your question? Are you okay, or do you need? Acceleration is not affected by the direction that the object is going. That's velocity. Acceleration is telling us what's happening to that velocity, right? So if we go back, right, let's go the part that's currently highlighted, okay? So Krista, from the velocity graph, first, positive or negative, from the part that's highlighted right now. Negative, it's below the x-axis, meaning that the object is going which way? In this case, down, right? Okay. Acceleration, positive or negative? Negative. Meaning, if we have a negative velocity and a negative acceleration, what should be physically happening to our object? Speeding up. And that's what the velocity graph shows us during that time. The ball is traveling downward. Gravity is pulling it downward, causing a downward acceleration. And therefore, it makes it go faster. Does that make sense? Let's say gravity is always pulling downward, because I'm going to fix that. In this case, it was negative because our motion detector was on the table, and up was positive and down was negative. In this case, yes. Okay. But then here, right? Let's go right through there. Okay. Velocity, positive or negative? Positive, so it's going upward, right? But the acceleration is negative. So positive velocity, negative acceleration, what happens? It's slowing down. The ball's traveling up, but gravity's pulling it down. Therefore, we're going to slow down. Okay? Does that make sense? Brett, go ahead. Yes. Because, remember, the acceleration is the change that's occurring, right? Gravity is always pulling it down. But depending on how it was currently moving, that could either cause it to slow down, like on the up trip, or speed up, like on the down trip. Acceleration is the change. What physically happens to the object depends on what it was doing when that change started. Okay, does that make sense? Krista, before we answer the questions, I want to show you these two graphs. Okay? So, I took these two graphs this morning, all right, doing exactly the same thing, tossing the volleyball up in the air and catching it at approximately the same place I threw it. But these graphs don't look the same as the graphs from before, right? What's different about them? Motion detector was high, right? And based on how the motion detector was oriented, downward is the positive direction and upward is the negative direction, right? So here, from here to here, right, the velocity is negative, but in that case, in the case where the motion detector was up high, that means it was moving upward. acceleration is what on this graph? Positive, because gravity's still pulling it down, but in this frame of reference, down is the negative, or down is the positive direction. But negative velocity, positive acceleration, physically what happened to the ball? Slowing down. Okay? So that's why we can't say that gravity's always negative. It's always downward, but what sign that gets depends on how we set up our frame of reference. Okay? All right, good there. Okay, let's answer some questions then from page 3 and 4. All right, so on page 3, question number 1 says, how closely does the coefficient of the quote-unquote t term compare to the accepted value for the acceleration of gravity on Earth for the volleyball? So, the coefficient of the t term, right, that's the number that shows up in front of t. For the volleyball, what number shows up in front of t in that equation? Negative 9.54. Okay? So, how closely does that compare to the acceleration of gravity here on Earth? Acceleration of gravity here on Earth being 9.81. Pretty close, right? We said that that value, 9.81 meters per second squared, is the acceleration caused by gravity, and gravity only. Was the volleyball under the influence of gravity and gravity only? No. We also have to deal with what? Air resistance. Although for the volleyball, and which shape it is, and how heavy it is, air resistance isn't a big factor. So, how closely does the coefficient, which is the slope of the velocity graph, right? How closely does that compare? They're pretty close. Why? Because there wasn't much air resistance, meaning gravity was the major factor affecting that volleyball. But they shouldn't be exactly the same because it wasn't gravity and gravity only affecting that volleyball.
If anyone has not had their picture taken, you may go to the PAC now. Thank you.
Good. Next chapter. Next chapter. That's what we're getting into. That's chapter 4. When we get into two-dimensional motion. Ooh. All right. Number 2. How closely does the average acceleration value compare to the slope of the velocity graph for the volleyball? So, the slope of the volleyball graph we established was negative 9.54 something, right? The average acceleration value for the volleyball that we calculated was negative 9.342. So, how close are they? Pretty close. Why? What are they both telling you? They're both telling you acceleration, right? Those are just two different ways of calculating acceleration. So if we're using the same graph, so the same motion, what should we find out about those two numbers? They should be the same, hopefully. Good there? Because, look, we're dealing with the uncertainty and the inaccuracy of the actual measurements that we took, right? That, we are dealing with air resistance, so they're not, exactly 9.81, right? But also, too, depending on what section I highlighted of the graph and how many points were actually included, we may not have had exactly the same points highlighted each time. So that may take our averages or our slopes a little bit different depending on how the LabQuest draws the best fit line. You know what I'm saying? That one data point a little bit off of that line can cause it to tilt just a little bit and make them a little differently. But, and we're also dealing with like those uncertainties in measurement, right? So, they're not going to be, they're very close but not exact. All right. Number 3. How closely does the slope of the beach ball graph compare to the slope of the velocity graph? The volleyball graph. So what do we see about the slope of the volleyball graph versus the slope of the beach ball graph? Which one's bigger? Volleyball graph, much bigger, right? Negative 9.54 for the volleyball graph, but the beach ball was only like negative 7 point something. What was it? 7.42, right? Why? We said that air resistance, right? Gravity causes the same acceleration to all objects, but that beach ball, much more prone, much more affected by air resistance. So we can't isolate gravity on that beach ball. We have to take into account that air resistance. And that slows the beach ball down. Its acceleration isn't as much as just with gravity. Because while they are the same shape, right, and they're both hollow, but the beach ball being lighter, right, when we get into chapter 5, we'll talk about terminal velocity. It's more affected by the air resistance. Air resistance depends on shape, it depends on the mass, and it depends on how fast you're going. The shape and the mass ratio of the beach ball makes it more prone to air resistance than volleyball does. All right, question number 4. Tricky. Make sure you pay attention to what it says. Was the effect of gravity on the beach ball different than the effect of gravity on the previous object? 2 objects. Use at least 3 objects in class. No. The effect of gravity wasn't any different. But the slopes of those graphs are different because we have to include air resistance in that discussion. So the effect of gravity is not any different, but in this situation we can't isolate only gravity. We have to take air resistance into account, and therefore we see a different effect on the beach ball. All right, good with those. All right, let's do this. Hopefully, because you filled it all together and we went over the answers to the questions together, that's an easy 10 points, right? Yeah. So, labs, let's put them into turn in place, okay? While you're up, in the green tray over on the side where graded things go, I graded your acceleration labs from last week, the one we did the cart going up and back down the hill. They are in the green tray over on the side. So if you would like to pick those up, I think there's also a couple of quizzes from last week that are still there. So go ahead and turn the lab from today in, pick up your old lab and your quiz if you have it, then we'll get back into reviewing 3.4. Okay, so over the past couple of days, we've been talking about section 3.4, and 3.4 deals with free fall. And we talked about free fall being when an object is in free fall, what's true about it? There's no effect other than gravity. Gravity and gravity only, okay? So we're going to do a couple of problems, a couple of examples dealing with that situation. So we're going to start on page 101, which is the end of section 3.4, the lesson check. And let's go through a couple of these. So if you want, the back of packet 3.4 is completely blank. So if you want to write down the answers to these questions there, you can. If you want to write it down in a separate sheet, you can. If you don't want to write them down, whatever, you got a test on Thursday, so, you know. All right, so let's start here. Question number 57. Question number 57 deals with the big idea about chapter 3. So it says, what property do all free-falling objects have in common? All freely falling objects have the same acceleration. Okay? The reason why that was the big idea of chapter 3 was because to get to that point, first we had to introduce what acceleration was, and then second we had to do what with constant acceleration. Okay? So all freely falling objects have the same constant acceleration. Okay? However, let's make sure we clarify. Number 55. 55 says, two rocks with different weights are dropped on the surface of the moon, where there is a near vacuum. How does the acceleration of the heavier rock compare to that of the lighter rock? They should be the same, because without an atmosphere in a near vacuum, the only thing that's affecting those rocks would then be what? Gravity from the moon. Okay? And we just talked about in 57 that gravity causes the same constant acceleration to all objects. Okay? Now, make sure we clarify. Here on Earth, the magnitude of that acceleration is 9.81 meters per second squared. If we can isolate gravity here on Earth, all objects will experience the same 9.81 meters per second squared acceleration. But on the moon, that magnitude is different. The acceleration of gravity on the moon is only about 1.6 meters per second squared. Both objects would experience the same 1.6 meters per second squared because they're both under the influence of the moon's gravity. So while we say that all objects under the influence of gravity experience the same constant acceleration, the magnitude of that acceleration depends on where we are. Okay? So don't think everywhere we go in the universe, the acceleration of gravity is 9.81 meters per second squared. Okay? Good? All right. 56. Why is a person doing a cannonball dive an example of free fall while a person descending to Earth on a parachute is not? Air resistance, right? We said, right? Brett, you said that free fall is we can isolate the effect of gravity and gravity only. For a person doing a cannonball, air resistance is pretty minimal. But for a person on a parachute, air resistance is not minimal. It's actually pretty important. It's how a parachute works. So. All right. Good with those three. Next, I would like you to open up your packet 3.4 to page 2. And at the top of page 2, right, is conceptual example 3.1, or 3.11, excuse me. So conceptual example 3.11 says, imagine dropping two rocks from rest, one after the other. When the first rock has fallen 4 meters, you drop a second rock. Maybe it has a little mark on the side, right? But for our purposes, let's say, Kaylin, we just wait a little bit and then you drop a second rock, okay? The 4 meters isn't as important in this case, okay? As the two rocks continue to free fall, does their separation increase, decrease, or stay the same? Okay? Elise? No, they're dropping it from the same height. They're just dropping it, drop one, wait a little bit, drop the second one. Okay? So it's saying, does the separation increase, decrease, or stay the same as they fall? All right? Yeah, they probably should have had, yeah. His hands are like at that little O, and I think that's yeah, because that's the origin. Okay. All right, so, Krista, do you have a question, or do you want to make a prediction? Okay. So, go ahead. Make your hypothesis, Krista. What is your educated guess about the answer to this question? Okay. Krista thinks that the separation increases. Okay? Let's go with it. Before we talk about whether your answer is right or not, let's draw a couple of pictures. Okay? Let's sketch ourselves a velocity versus time graph for these two rocks. We'll call the red rock rock 1 and the blue rock rock 2. Yes. Okay. That's what free fall is, right? Free fall is a constant acceleration, right? Kayla, is that okay? Yeah. Okay. Brett, go ahead. Like on the earth? No, I mean, maybe a little bit, but that's not going to be essential to our answer because regardless of where we are on the earth, even if the acceleration of these objects is slightly different than 9.81, they would both experience that same slightly different acceleration. So the answer really wouldn't depend on where we were. Okay? All right. Are you good? Or? Yeah, I know. Then maybe they should have went to a higher bridge, but, whatever. All right. What's the red rock's velocity graph going to look like for this situation? Brett. It's going to start from 0 because what was the rock doing right when we let it go? Nothing. And then, Caitlin, like we talked about, right? What happens to the velocity of that red rock as it falls? It's constantly increasing because it experiences a constant acceleration. Okay? In real life, yes. But if we could isolate only the effect of gravity, no. It would just keep continuing to increase more and more and more and more. But here on Earth, we don't experience that. Right? But on Earth, because of air resistance, yes, there is a point where, and we'll talk about that more in Chapter 5 when we talk about forces. Okay? Yes, Luke? That's terminal velocity. Because there comes a point where the air resistance exactly balances out how hard gravity is pulling on you. And if you have one force pushing up on you and one force pushing down on you exactly the same, you don't go any faster. Okay. Okay. All right, Brett, good. The blue one starts a little bit later, right? Because we drop it after a certain amount of time. But Brett, after we drop it, what starts happening to its velocity? It increases at a nice consistent rate. Okay? What could we say about those two lines? They are parallel lines. Why? Because they have the same slope. Why? Because what does the slope on this graph tell us? Acceleration. Okay? Good there. All right. But remember, this graph is asking us, or this problem is asking us about separation. And this graph is given, this sketch that I had you draw was more about velocity, right? So let's draw ourselves a second graph. A position versus time graph. Okay? Krista, to highlight a point or make another point what we talked about earlier, right? The way that this picture is set up, they've called the origin up here on the bridge, and the arrow is pointing downward, so they call that the positive direction. So these velocities are increasing in the positive direction, and the slope of this graph is positive because gravity's pulling it down, and that's the positive direction in this picture. Okay? So that's why that graph looks like that. Right? All right. Position graph. First, what do position graphs for constantly accelerating objects look like? Position graph for a constantly accelerating object is a parabolic curve, a parabola, right? So the red one is going to start here, right? And it's going to look like that. Mr. Horline is mixing up some chemicals for lab tomorrow, so that's the little stand that it's on. Yeah, it's got a magnet in the bottom that just spins, and you put another magnet in there, Mr. Horvath's mixing up some things for tomorrow. So his hood is all dirty because he did a demonstration on the first day of school and never cleaned it up. So using mine. So all right, blue position graph. Blue position graph is going to look like what? It's going to start later, but once it does start, what's it going to look like? It's going to look the same, right? Because it's constantly accelerating as well. Okay? Good with those pictures so far. Okay. Now, let's answer the question and find out whether Krista was right. That purple line that I just drew on that graph represents what? Which distance between the red and the blue? When what happened? When the blue one was dropped. So, how long is that purple line? This purple line represents 4 meters, right? Is that better? All right. Are you ready? Okay. While we don't know exactly how long that second purple line is, how long is it compared to the first purple line? It's longer, right? Meaning, how far apart are red and blue now? Further apart than 4 meters. So Kayla, do you understand that the first purple line is 4 meters? Because remember, this is a position graph, so it's telling us where, right? Here, they start 4 meters apart. The second purple line, right, because it's longer than the first purple line, means now they are farther apart, okay? So, their separation increases, okay? If we go back to something that we talked about yesterday with with the volleyball graphs. In packet 3.4, page 3 up at the top, position and velocity change differently in free fall. Velocity increases linearly. So when we look at those velocity graphs, they stay the same distance apart, or they stay the same separation in velocity. Red won't get any more faster than it is blue anywhere along the trip. But if you're going faster, here's my example. You're on the highway. You're going 60 miles per hour. Another car is going 50 miles per hour. You're going to pull away from that car because you're going faster, right? If he speeds up from 50 to 55, but you speed up from 60 to 65, you're already going faster than him, right? And now you're going faster even more, right? You're going to pull even farther away from that car, right? Good there? Because, like it says in packet 3.4, right? Velocity changes linearly with time, but distance increases with time squared. So if we talk about time intervals, those distances keep getting bigger and bigger and bigger and bigger at a faster rate than the velocity does. Even though the velocity is changing by the same amount each time, because you're already going faster, and now you're going even more faster, right? You just keep increasing that separation. Okay? Good there? All right. I'd remember that one.
Well, I mean, I get the basic concept. I don't, but like, do I need to know all of the numbers and stuff?
No. If you get the concept of it and you can apply it to a different situation, that would be good. So, but I would maybe keep that one in mind when you're studying, whether it be tonight or tomorrow. Go ahead, Brett. Yep. Technically, it never goes straight up. Yeah, that's just me. That's just the way I drew it, you know. But technically, on a parabola, if you continue that trend, a parabola never goes straight up. It gets very, very steep, but it never goes straight up. Okay? Because for it to go straight up, that means that there would be two y values for the same x value. Does that make sense? And that can't happen, you know, in a parabola, just the way the equation works. And if we're talking about a position graph, if it went straight up, that would mean you would have two positions for the same time, and you can't have that. Yeah, that's just the way I drew it, but... All right, two more here. Let's go back to page 101. Back to page 101. And question number 59. It says, a girl on a backyard trampoline bounces straight upward with an initial velocity of 4.5 meters per second. What's the girl's velocity when she returns to the trampoline? The chart that we filled in yesterday on your lab, we took the velocity at 3 separate points along the flight of the ball, right? We took the velocity, let's go. We took the velocity here, here, and here, right? And if you remember, hopefully you remember, maybe you don't, but the velocity on the way up and the velocity on the way down were the same, except one's positive, one's negative. That constant acceleration from gravity causes a symmetry within the measurements that we use to describe that acceleration. So if the girl left the trampoline with a speed of 4.5 meters per second, how fast is she going when she gets back to the trampoline? Negative 4.5 meters per second, because of the symmetry caused by that constant acceleration. Good there? All right, I wanted to do one more example problem with you guys, so that we have put some numbers onto this. And that example problem is number 61 on that same page about a lava bomb. Yeah. It does sound intense. Hey, I don't come up with the names of these things, so you're going to have to ask the geologists about that one. So. All right, it says, a volcano launches a lava bomb straight upward with an initial speed of 28 meters per second. Taking upward to be the positive direction, find the speed and direction of motion of the lava bomb 2 seconds and 3 seconds after it's launched. So, we are running out of time, so I'm just going to walk you guys through this one, okay? If it says, find the speed and direction after, what is it asking you to solve for? Final velocity, right? Initial speed of 28 meters per second upward, taking upward to be the positive direction. Okay. Time 2 seconds. Acceleration at this point, negative 9.81 meters per second squared. Because it's being caused by gravity. But which way does gravity pull things? Down. And if we called up the positive direction in this problem, down is the negative direction. So we have a positive velocity and a negative acceleration. What's going to happen to the lava bomb? It's going to slow down first, okay? So, based on this information, you go to page 88 of your book, or you look at table 3.3 that has all those equations of constant acceleration motion, and you find out that VF equals VI plus A times T. Now, important for solving this problem, you cannot change the equation. You can plug numbers into the equation, but you can't change it. VF is VF, that's what we're solving for. Here, we're plugging in positive 28s. Then, plus, you can't change that, but you can plug in negative 9.81 here and 2 here. Okay? When you solve this, you get positive 8.4 meters per second. Meaning, which way is the lava bomb still going? Up. But, for the next part, okay, all of these numbers stay the same that we've written down except for the time. So, for part B, you would still solve for VF. Initial velocity is still positive 28 plus negative 9.81 for the acceleration. Okay? Oop. And when you solve that, I believe you get negative 1.4. The fact that it's negative 1.4 tells you what about this lava bomb? It's already reached the top and it's starting to come back down. So you can't change the equation, but you can plug negative numbers into that equation. Solve for what the final velocity is, the sign will tell you what you need to know. Okay? Tonight, there is a homework assignment on the calendar. Bell's going to ring. It is... It's more questions similar to the ones we just did in class. Answers are posted online. Okay, if you need a little more practice. I'll show you that real quick. Okay, so.